graph, a cut edge or bridge, it's a nicer word, in a connected graph is an edge that, when removed, disconnects, makes the graph not connected, so disconnects the graph. First example, look at this graph C6. Is this edge a bridge? I see some nodding. No, it's not a bridge, because if I remove this edge, what happens is the graph is still connected. It's the same as just putting 6 vertices on a string. It's like a necklace, right? You take the necklace off, it's still connected, it doesn't drop into 2 pieces. So this is not a bridge. But if you took this graph, and I don't know if this has a name, it's an example of what's called a tree. I'll define trees later, but a tree is a connected graph with no cycles. In a tree, it turns out that you remove any edge, and any edge is a bridge. Clearly, if I remove any of these edges, it's a bridge, because the necklace will then fall apart. What was the necklace will now fall apart. Okay? Here's a slightly trickier example. Here's a graph. How many bridges does that graph have? How many bridges does that bottom graph have? That's 8 vertices. One's wrong. 2 is correct, because I think you can all spot that this is a bridge. I use this symbol to mean it's a bridge. That's a bridge. But this is also a bridge, because if I remove this edge, I'm not removing vertices, I'm just removing edges. If I remove that edge, I'm left with, forget the first one, if I remove that edge, I'm left with an isolated vertex, which is a graph and a component, and the rest of it. Okay, so there are 2 bridges. Well, I mentioned trees, so let me now tell you what a tree is. So a tree, definition. There's different definitions. A tree is a connected graph with no cycles. The word no cycles, you sometimes see this written as acyclic. Acyclic. It has to be connected, that's crucial, and it has no cycle. Why is it called a tree? Well, you normally sort of select one vertex and call that, you distinguish one vertex. You don't have to, but often trees, in applications, you choose one vertex called the root, and then you have edges emanating from that. Might be like this. sort of first generation, and then you keep going, you can have edges emanating from that. You don't have to have them all. There's an example of a tree. I'll stop there. That's an example of a tree. Okay, you can distinguish a vertex and call it the root sometimes. Of course, you should do it upside down if you want to think of a real tree, but it's normally convenient to do it this way. And the vertices with degree 1, so what are the degrees here? That has degree 4, 3, 1, 1. Vertices of degree 1 are called leaves, if you want, for obvious reasons. Okay? Now notice that it is true that, well, before I go on, let's just count the vertices and the edges here, which I've done this thing at random. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 vertices. So remember, I use n normally for the number of vertices, not little v, because v is a vertex. So this is 12, did I say? 4, 12. Sorry. How many edges? Well, I do use E normally for the number of edges, although I shouldn't perhaps do so. The number of edges is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and it's always true in a tree that the number of edges is always equal to the number of vertices minus 1 for a tree, in a tree. I'm not going to prove that today. Now you can always remember this just by drawing a simple tree. You can just, this is a tree, and it has 2 vertices and 1 edge. Or you can be even simpler. This is a tree. It has 1 vertex on its own. The people who like isolated vertices, that's a tree. And it has 1 vertex and no edges. So with these simple examples, you can always remember to get this formula the right way round. And then you can prove it by induction. You can prove this by induction, can be proved by induction, on the number of edges. It's okay to start with, and then if you've got a graph which is a tree, you can then remove. There has to be, if you think about it, there has to be a vertex of degree 1 in a tree, because otherwise you could keep going and get a cycle. Can be proved by induction, using existence, using the fact that there exists at least 1 vertex of degree 1. So you can take that vertex, you can remove it, you can remove the corresponding edge, you've then got a tree with a smaller number of vertices, you can use induction. And this formula will remain valid because you've only removed 1 vertex and 1 edge. So I'll leave you to write that out as an exercise. I just want to remark that there is this lemma, which maybe I can convince you of. There are different definitions of trees. And in terms of, I was talking about bridges. So any edge of a tree is a bridge. So look at the picture above. You just see anything I care, any edge you choose, if you remove it, you're disconnecting the graph. If you remove this edge here, you're leaving an isolated vertex. If you remove this edge here, you left a piece here. So you'll always split the graph up if you remove 1 edge, any 1 edge. Any edge is a cut edge or bridge. Why is that? Why does that follow from... Maybe that's if and only if, but I'm just going to prove it this way. Why does that follow from the definition? Proof. So if this convinces you. This is the sort of thing you could be asked in an exam because the proof's quite short. So suppose we want to prove that, suppose we have an edge UV connecting vertices U and V. Suppose this is an edge of our tree. So U and V are vertices. Notice the tree can't have multiple edges. It has to be simple because we've got no cycles. As soon as you have multiple edges or loops, you have a cycle. So that's excluded. So the tree has to be simple. So if there is an edge between two vertices, it's unique. So this notation is okay because there can't be more than one edge between two vertices. Okay, suppose this is not a bridge. Suppose UV is not a bridge. Then when we remove it, when removed, the graph is still connected. So we can find a path, we can walk from U to V. So when removed, we can still walk, find a walk through the edges from vertex U to vertex V. And that implies that there exists a path. Remember, a path you don't go over an edge more than once. But if you can walk from U to V, you might go over edges more than once. But you can always get rid of that by eliminating detours. So that means there is a path. So that implies that there exists a path from U to V. Without, I'm not going through this edge which I've removed. So this has been removed. But if you have a path from U to V, that implies that if we replace the edge, that implies that there exists a cycle. When we replace, we put back UV into the graph, we get a cycle. And that's a contradiction because we're assuming it's a tree that has no cycle. Let me just draw a picture to illustrate what I'm saying. So here we've got U and V. Maybe this is U and this is V. And as part of our tree, we may have other vertices like this. And we're going to remove this. The first step is to remove, we're supposing this is not a bridge. We're going to remove UV. And that means what we get is still connected. That means there must be a path from U to V. We don't know, there are other bits of the graph I haven't drawn, but there must be a way of getting from U to V without going through that red cross, because the graph is still connected. Okay? Because we're assuming that it's not a bridge. It's not a bridge. What we get when we remove it is still connected. But then I've got a path that goes from U somehow and gets back to V. That's our path. But then if I throw in this edge again, I've got a cycle. Okay? So the whole thing then gives you a cycle. And that's the contradiction. So for that reason, it's a very useful fact. If you have a tree, any edge, when you remove it, it disconnects the tree and it's no longer a tree. Okay, so I'm going to describe something called Fluores Algorithm for constructing for constructing or for finding a Eulerian or also semi-Eulerian, if you don't have Eulerian trail. And let me hide what's on the, for the moment what's on the right. There's the example, applied to this example. Now, the first thing you do when you're asked, is there a Eulerian trail, you look at the vertex degrees. And here, if you start at the bottom, it's looking good because they all have even degrees. But this, unfortunately, the red one has degree 3, and also the green one has degree 3. So this does not have, this graph, it does not have a, what's that squiggle? 2, it's meant to be. It does not have an Eulerian trail. But it does have a semi-Eulerian trail because we've only got 2 vertices, can't have 1 vertex of odd degree, we've only got 2 vertices of odd degree. So in this example, we have 2 vertices, let's call them odd vertices, meaning of odd degree. So what do we do? I want to start at 1. You have to start at 1 and finish at the other. So we're going to start at the green one and finish at the red one. So in this algorithm, you just go where you want to. Okay? So you start walking, as before, from your starting point. And what happens here is I've decided to start diagonally. Then I've decided to go down here. Then I've decided to keep going down. I could have gone across, but I've gone down. And then I've gone up here. So I've got to this vertex. Okay. Now you have to try and remember what you've done already. So you sort of mentally in your mind, you remove the edges you've already traversed, because you can't go back on edges. Okay, I've got another one here I've removed. Leave it like that. And then you look at the remaining graph, and I've got to this vertex, and I want to know where to go from this vertex here. Okay, so I've got to this vertex. I look at what's left of the graph, which includes this edge there at the top. And you see that if I were to go up this edge here, I'd be stuck. I'd already be at the finish. I could have gone around there to get to, I could still tackle this square at the top, but I wouldn't ever be able to do the triangle at the bottom. If I decided to go up here, so I'm asking the question, should I use this spare edge? I haven't used it yet. I've got to this point there with the question mark. Should I go upwards? And the answer is obviously no, because if I go upwards, I can't do the bottom triangle. And the problem is that this thing with the question mark here, this is a bridge. It's a bridge not for the original graph, but for the graph you've got to at this stage of the game. Okay, and so if you look at that graph in which I've removed with the pens the various edges, we have, if I remove this edge, I get 2 components and it's a bridge. So obviously I can't go along a bridge. I have to first of all do another choice until I'm forced to. So the idea is, here's a better picture in which the grey shows, you should really think of the grey as being removed, and you see if you remove the grey, this does become a bridge. This edge becomes a bridge. So when you avoid bridges, the algorithm basically says, there's just one basic idea. First of all, you must start at an odd vertex if there is one. This is for semi-Eulerian trail, otherwise there's no hope. A vertex of odd degree if there is one. Otherwise it doesn't matter. That's the first principle. The second principle is you avoid a bridge. Having removed, let's say, having removed the edges you've already crossed, having removed the edges already, what's the word, traversed, avoid any bridge where possible. Okay, so again, we get to this point here, we don't know what to do, but you say, having removed the grey stuff, this is a bridge, so we're not allowed to go across it unless we've done other things. So we don't choose this, we don't choose that direction. We can either choose that direction or this one, it doesn't matter. If I go right, I can then finish the triangle. Now the triangle has been removed, the triangle has gone grey, and at that point, you also remove isolated vertices, so you need to also remove, having removed edges already traversed and asterisk, and isolated vertices. It's explained properly in the notes. So this would have all been removed, all the stuff now has been removed at the bottom, and so this is no longer a bridge actually, and we can go along it. And then we can finish the Eulerian trail. Okay, so that is another algorithm. It's less effective computationally, but it's easy to understand. Maybe you just keep walking and never take a bridge until you're forced to. Okay. Well, by the time you're forced to, it will no longer be a bridge actually.